Hi, everybody. Welcome to the spring's first UMass CS Systems Lunch. I'm really thrilled to have Işıl Dillig here, visiting us from Texas, apparently from a giant crowded library. So Işıl is going to be talking about computer-aided programming across the software stack. Just a little bit about Işıl. So Işıl is an associate professor of computer science at UT Austin, where she leads the UToPiA research group. Her main research area is programming languages with a specific emphasis on program synthesis and static analysis. The techniques developed by our group aim to make software systems more reliable, secure, and easier to build in a robust way. She has won numerous awards. She's, of course, it would take too long to go through all of the things, all the accolades. Just briefly, she is a Sloan Fellow. She's won an NSF CAREER Award, and she is a proud alumna of Stanford University, with the rare trifecta of a bachelor's, an MS, and a PhD, all from Stanford. All right, with that, I will let you take it away, Işıl.
Hi, everyone. Well, thank you very much for the kind introduction, Emery, and thank you for inviting me to give a talk here today. So today I want to talk about some of the work that we've been doing in my group on program synthesis. And in particular, I want to emphasize how it can help with various tasks across the entire software stack. And I also want to kind of illustrate how program synthesis can help with cross-cutting concerns in software development. Oops. Just give me 1 second. All right, here we go. Okay. So first of all, for those of you who may not be very familiar with program synthesis, the goal, of course, here is to generate an executable program from some sort of high-level specification. And here, when I use the term specification, this should be construed very broadly. It can mean a whole variety of things. So for example, on the more formal side, it can be logical specifications. It could be a reference implementation, or on the more informal side, it can be test cases, input-output examples, and even natural language. Now, as it turns out, program synthesis is by no means a new problem. In fact, there are papers from the 1970s, such as this paper by Zoher Mana and Richard Waldinger, where they present program synthesis as a means of turning your dreams into programs. However, even though the idea of program synthesis is fairly old, I think it would be fair to say that this has not been an active research area for maybe 20 to 25 years. But of course, as you may have noticed over the last decade or so, there has been a huge renaissance in this field. So before I go into the work from my group, I just want to first kind of take a few minutes to talk about why this is the case, what has led to this big renaissance in program synthesis. So I believe that from a technical perspective, there are two reasons that explain this big comeback of program synthesis. And one of those reasons, in my opinion, is all the progress that we have made on automated program analysis and automated theorem proving, particularly in the context of SAT and SMT solvers. And if you're wondering how that's relevant, well, program synthesis is fundamentally an extremely difficult search problem where you need to look through a massive space of programs. And the idea here is that we can use automated program analysis and constraint solving techniques to significantly prune the search space. Now, another reason that explains the big success of program synthesis is, of course, the machine learning revolution. And in particular, just as automated program analysis and theorem proving techniques allow you to prune the search space, machine learning techniques help us prioritize the search and navigate the search space in a much more intelligent way. And these two secret sauces, namely this combination of program analysis and theorem proving and machine learning, this is something that we're going to see as recurring themes in various parts of this talk. Okay. So with that said, I want to now kind of dive into some of the work in my group. And in particular, as I mentioned earlier, my goal here is to illustrate how synthesis is useful across the whole software stack, starting from end users going down to application developers, and then going all the way down to systems programmers. And in addition, I also want to showcase how program synthesis helps with many different concerns in software development. This includes, of course, developing new functionality, but it also includes maintaining software, helping with performance and security concerns, as well as, of course, correctness. Okay, so to get us started, I want to focus on the top of the software stack, namely non-programmers. And in the context of end users, there have, of course, been many success stories of program synthesis. But for the purposes of this talk, I want to focus on one of my favorite application domains, which is data science. So as we all know, the main goal of data science is to gain insights from data and to do useful predictions. And if you think of data science, the main techniques that you might think of are probably machine learning and visualization. But actually, in reality, it turns out that data scientists spend the majority of their time, and according to some sources, like 80% of their time, on various data preparation tasks like data wrangling, data imputation, cleaning, and so on. So based on this observation, a bunch of the recent work from my group has developed program synthesis techniques for automating various aspects of data science, including data wrangling, imputation, visualization, and so on. And we published a series of papers on this topic. But for this talk, I just want to focus on one of these tasks, namely data wrangling, and I want to talk about why it's useful and how we can use program synthesis to automate data wrangling tasks. So to kind of give a high-level overview, basically when people talk about data wrangling, this refers to some sort of transformation. So you may have some data, some raw data in some tabular format like a CSV file or data frame. But in order to do some downstream machine learning or visualization task using your favorite library, you typically need to transform it to some other format. So for instance, this long format that you see on the right side of the slide. And if you stare at this for a second, you may realize that this is a non-trivial transformation. First of all, because it requires reshaping the table. The source and target tables have different numbers of rows and columns. But also observe that in the process of this transformation, you need to append the contents of the table to column names. And in fact, if you go ahead and look at online forums like Stack Overflow, Stack Exchange, and so on, you will see that there are literally maybe hundreds of questions where data scientists ask questions about how to perform some data wrangling tasks. So this is where our work comes into play. In particular, in our recent work, we proposed a bunch of programming by example techniques that aim to automate data wrangling. And as is typical in programming by example, the user, of course, conveys their intent using simple input-output examples. So for instance, a small input table and a small output table. And it turns out that programming by example is a good fit for this task for two reasons. First, in the context of data wrangling, these examples are actually easy for end users and data scientists to construct. So if you look at these online forums like Stack Overflow, pretty much every post already comes with a simple input-output example. And furthermore, even though examples are generally a very under-constrained form of specification, unlike some other domains that I worked on, for example, regular expression synthesis, for the purpose of this domain, we can often successfully infer the user's intent just based on small input-output examples for this domain. Okay, so based on these observations, we've been developing programming by example engines and new techniques that aim to automate this task. And the idea here is basically, given these input-output examples, we synthesize this data wrangling program, and then the user can apply this data wrangling program to their original, much larger data set, and they can obtain their desired data frame. Okay, so hopefully everyone agrees with me that this is a useful problem. Now I want to tell you a little bit about how we actually do this. So a lot of the techniques that we've developed for this domain are based on top-down enumerative search, but they combine these two secret sauces that I alluded to in the beginning, namely a combination of machine learning and automated program analysis / theorem proving. So in particular, since we're doing top-down enumerative search, at every step we have some partial program. So you can think of this as some abstract syntax tree where some nodes on the in the abstract syntax tree are unknown, so indicated by these question marks in my drawing here. So now what we do at every step, we're going to use some statistical model that we've trained offline to figure out how we should expand this partial program. And the details of this model are not terribly important, but here I'm assuming that we have some model that basically, given your current partial program and the specification, it gives you a probability distribution over productions in the grammar. So in other words, it tells you how to expand this partial program. So for instance, in this example here, our machine learning model might say a useful thing to do is to instantiate node N2 with the filter construct. So now once we have this expanded partial program, this is where this idea of program analysis comes into play, because what we're going to do is we're going to use the abstract semantics of all these constructs in our domain-specific language to check whether this partial program is feasible or not. Okay, so this uses a combination of program analysis techniques and SMT solvers. And in this example, it turns out that this partial program is indeed feasible. So we go back to the search phase and keep expanding our partial program. So for instance, in the next step, our machine learning model may say a useful thing to do is to instantiate node N4 with our input variable, let's say X. And again, we go back to our deduction engine and again ask, is this partial program feasible? And now it can tell us this is infeasible. And intuitively, to see why that's the case, observe that all the constructs used in this partial program preserve elements in the input data structure. But if you look at the specification on the left-hand side, we see that the output is actually something that's not part of the input. So therefore, we can say, no matter how you instantiate these question marks, there is no completion of this partial program that will satisfy the specification. And beyond just giving a yes/no signal, we've actually developed deduction techniques that can also learn from these kind of conflicts. So they can basically infer a bunch of other infeasible partial programs that are infeasible for the same reason. And we can use this information to update our machine learning model using reinforcement learning. And this allows us to progressively improve our model guided by the deduction engine. So in other words, this allows us to achieve some sort of synergy between deductive reasoning and machine learning. Okay, so now let's talk a little bit about how this works in practice. So to evaluate this approach, we collected 80 data wrangling tasks from online forums, primarily Stack Overflow. And if you're wondering whether these tasks are simple or not, we actually did a small-scale user study. And what we found that a lot of these tasks are highly non-trivial. And in fact, a bunch of them cannot be solved by people with significant data science experience in a significant amount of time. And the cool thing here is that the synthesizers we developed can actually solve 78 of these 80 tasks, so basically all of them except 2. And furthermore, they can do so in a reasonable amount of time. So the average running time of the synthesizer is in the order of a few seconds. Okay, so now that concludes kind of this data science related part of the talk. So now I want to move down one level in our software stack. And now I want to illustrate how computer-aided programming can help application developers. And to illustrate this, I want to focus on database applications, which, as you all know, are programs that interact with an underlying database. And we were interested in this domain because database applications are everywhere, right? So web applications, enterprise software, all of these interact with some underlying database. And as you may know, because these database applications are so common, there's quite a bit of infrastructure around them. There are a bunch of frameworks like Ruby on Rails, PHP, MySQL, Django, and so on that aim to simplify the development of these database applications. Now, however, it turns out that despite the existence of all this ecosystem, one common pain point during the evolution of database applications is what people refer to as schema refactoring. So your original application uses one schema, but then as this application evolves, you realize that you need to make some significant modifications to your database schema. So let me give a few examples. So one common type of refactoring is splitting tables. So you may have one table, let's say that's large, that's causing performance problems. You may decide that you need to split it into multiple tables. Another example, which is the dual of splitting, is of course merging tables. So you may have two tables that are frequently being accessed together. So to avoid expensive join operations, you may decide to merge these tables. And another example is denormalization, which means that you explicitly introduce redundancies, typically to improve the read performance of the application. Okay, so now even though these kinds of schema refactoring scenarios are quite common, from a software engineering perspective, they're actually quite a bit of a pain in the neck. And the reason for that is whenever you change the schema, there are two things you need to worry about. So first, you need to migrate the data, meaning you need to move it from the source to the target schema. And in addition, you of course need to migrate the code, meaning that you need to re-implement all parts of the program that are affected by the schema change. And among these two problems, data migration has already there's already some support for automation, and it's also somewhat similar to the data wrangling domain that we talked about earlier. So in this part of the talk, I want to focus on the code migration aspect, which is currently done manually. Okay. So basically, in our recent work, to address this problem, we developed a synthesis technique and its implementation in a tool called Migrator that takes as input a database application and a new schema. And it automatically synthesizes a new program that uses the new schema. And furthermore, we guarantee that the original and new program are provably equivalent to each other. So I'm going to tell you a little bit about how this works. And this segment of the talk will be based on our paper from PLDI 19 called Synthesizing Database Applications for Schema Refactoring. So before I tell you how this works, so first I want to give you an example to illustrate what I mean by code migration. So here on this slide, I'm showing you a tiny fragment of a database application. And as you can see here, this database application allows you to create subscribers, update subscribers, and it also allows you to query information about different subscribers. And if you focus on this for just a second, you will see that this program interacts with a database table called subscriber, which stores information about subscribers, their ID, name, and it also has a column called filter. And this stores basically a large XML file that describes the conditions under which each subscriber will be notified. So now it turns out that during the life cycle of this application, and this is actually something that we found in a GitHub commit, the developers decide to split this table into two separate tables. So in particular, they introduce this new table called filter, and they introduce a column called FID_FK that stores a foreign key that points to the relevant row in the filter table. And obviously, if you change the database schema like this, you also need to re-implement the code. And as you can see on this slide, the implementation of our program now becomes a little bit more complicated. It has nested queries, join operations, and so on. Okay, so now that we know the problem that we're trying to solve, I want to talk a little bit about how this actually works under the hood. So again, this is another example of where we combine these two ingredients, namely both a combination of machine learning and deductive reasoning. And from a high level, our approach works as follows. So first, we take the source and target schemas, and using fairly lightweight natural language processing techniques, we conjecture a likely value correspondence. So basically a mapping from attributes in the source schema to attributes in the target schema, okay? And the reason we do that, once you have a value correspondence, we can use it to generate a program sketch. And in our context, a program sketch is basically a database applications where everything is known except database elements. So we can have unknowns that correspond to join expressions, names of tables, names of columns, and so on. And then once we have this sketch, we invoke a sketch solver, and this is where the lion's share of the work is actually done. And the sketch solver it basically uses a combination of search, program analysis, and program verification to try to complete the sketch. So in other words, it tries to find an instantiation of the sketch that's equivalent to the original program. And of course, there's a program verification component under the hood. And if this succeeds, we return a target program. On the other hand, if we prove that there is no completion of the sketch that's equivalent, we backtrack and we conjecture the next most likely value correspondence. And we keep going until we either run out of value correspondences or we finally find the desired program. Okay, so now let's talk about how this works in practice. So to evaluate our approach, we collected 20 database schema refactoring scenarios, and about half of these benchmarks are taken from kind of textbook examples, and the remaining half are taken from real Ruby on Rails applications that we found on GitHub. So in particular, we looked for GitHub commits that involved a change to the schema, and then we tried to use our tool migrator to automatically generate the new version of the application. And the main result here is that our tool was able to generate equivalent programs for all of the benchmarks except one. And the reason that one failed was because because of a limitation on the program verifier. So in particular, we actually did enumerate the correct program, but we failed to verify it using our existing verification technique. And in terms of whether this is practical, well, unlike the data wrangling situation that's where synthesis time is just a matter of seconds, the running time here is significantly more, but still it's practical. It takes about 3 minutes on average for applications that have, let's say, a few hundred or SQL statements. All right. So now, in the last half of the talk, I want to move all the way down to in the software. I want to move all the way down on the software stack, and I want to talk about how computer-aided programming can help systems programmers. And in this part of the talk, I particularly want to emphasize how synthesis techniques can also help with performance and security concerns. And to illustrate that, I want to focus on a particularly challenging scenario, which, as we all know, is concurrent programming. And as anyone who's written concurrent programs knows, this is a very difficult problem. And one common source of bugs when you write multi-threaded code is if threads need to have signaling between them, but there is improper or missing signal. So, for example, let's say there is one thread that's blocked on something, and it's waiting for some other thread to signal it to continue, but those threads either forget to signal it or signal at the wrong time. This is, of course, going to result in nasty problems like deadlocks. So now in this part of the talk, I want to show you how program synthesis techniques can simplify the development of concurrent programs. And this segment of the talk will be based on our PLDI 18 paper called Symbolic Reasoning for Automatic Signal Placement. So basically, the idea here is that rather than asking programmers to write low-level concurrent code that involves things like semaphores or condition variables, we're going to expose a much simpler programming model that does not involve explicit signaling between threads. And in particular, what we're going to do is we're going to provide a construct called wait until. And basically, you say wait until some predicate, and basically one thread is telling the other threads that they want to be blocked until that predicate becomes true. But the difference here is that rather than having the other threads explicitly signal each other, we're going to build a synthesis technique that's going to automatically insert any necessary signaling operations. And furthermore, we're going to do this in a way that guarantees the absence of deadlocks and data races. And of course, we're going to do our best to achieve good performance that's competitive with handwritten code. So before I talk about how we do this, again, let me give you a simple example. So here I'm showing you a simple readers-writers lock that's implemented using our proposed programming paradigm, which I refer to as an implicit signal monitor. And as you can see here, there are no condition variables, there is no signaling, the code just uses this simple wait until construct. And our goal here is to take this implicit signal monitor, and we want to generate its explicit signaling version that does indeed introduce condition variables and where there is explicit signaling between threads, as you can see from the highlighted parts of the code. Okay. So now let me talk about how we actually do this. So the key idea here is to reduce all these signaling decisions that we need to make to a bunch of small program verification problems. So we're going to reduce it to proving a bunch of Hoare triples. And in more detail, what we're going to do is first, given the input implicit signal monitor, our first step is to infer a so-called monitor invariant. So this is going to be a formula that holds every time a thread enters and leaves the monitor. So then, given this monitor, we're going to look at all the conditional critical regions in our code and all the predicates that are mentioned in some wait until predicates, and we're going to make a sequence of decisions. And the first thing we need to decide is, given some conditional critical region or segment S, at the end of this segment, do we need to signal all the threads that are blocked on P? Okay. And to answer this question, we generate this little program verification problem, so this Hoare triple. So what this is saying is, assume that before we execute our segment S, assume that the monitor invariant holds, which you already proved that it does. And we assume that P is false, meaning that some thread is blocked on P. So after executing S, can we prove that P continues to be false? And if that's the case, well, if we wake up a thread, well, we know that P is still false, so they won't be able to make progress. So if this Hoare triple is valid, that means there is no need to signal. On the other hand, if we cannot discharge this Hoare triple, we still need to make two important decisions. So the first decision, the second decision we need to make is, can we signal unconditionally, or do we need to insert a runtime check? And to answer that question, we again generate a small program verification problem. So this time we ask the question, assume again that P is false, meaning a thread is blocked on P. After we execute S, can we guarantee that P becomes true? So if this is the case, we know that if we wake up a thread, they will definitely be able to make progress. So we can go ahead and signal unconditionally. But if we cannot prove it and we signal, then this may result in, well, this will probably result in an unnecessary context switch, which is expensive and we want to avoid. So if we cannot discharge this Hoare triple, rather than just unconditionally waking up a thread, we insert a runtime check and we test whether P is true before performing a signaling operation. And finally, the last decision we need to make is, do we need to signal or do we need to broadcast? Meaning, do we need to wake up just one thread, or do we need to wake up all threads that are blocked on this predicate? And again, to answer that question, this is a little bit more complicated, but not too bad. So in this case, we're going to generate a series of program verification problems, one for each thread that's waiting on P. And in particular, what we're going to ask is we're going to consider all these segments that are nested inside the wait until P predicate. So basically, we consider all the threads that are blocked on P, and we ask the following question. So assuming P holds, assuming we've woken up a thread that was blocked on P and now that's now able to make progress, after we execute the critical region of that thread, does P become false? Because if that's the case, if that's true for all the threads that are blocked on P, that means only one thread will be able to make progress. So we should only be waking up one. But if we cannot discharge this for all threads, then that means we need to do a broadcast operation. There may be multiple threads who can make progress. Okay. So obviously the technique that I described so far is correct by construction. It will ensure that there are no deadlocks, but the obvious question is the synthesized code actually efficient? How does this compare with manually written code? So to answer this question, we collected basically a bunch of Java programs that implement monitors. And we compared our approach against both the original manually written code, so that does explicit signaling, and we also compared our technique against a prior approach called autosync. And in a nutshell, autosync supports the same kind of programming model. It also allows these implicit signal monitors, but rather than doing program synthesis, rather than generating explicit signaling code, it instead inserts runtime checks. So everything in autosync is done runtime. It's a fully runtime technique. So now to see what's going on, let's kind of zoom into one of these plots here. So here on the x-axis, I'm showing the number of threads, and on the y-axis, we're looking at milliseconds per operation. So obviously, the lower, the better. And what you see here is that the code that's generated by Espresso, the blue line, is actually very competitive with the handwritten explicit signaling code. And furthermore, as you can see from the gap between Espresso and the prior technique autosync, this approach does significantly better than the prior state-of-the-art runtime approach. And if you look at the other benchmarks, we see that the same trend continues pretty much for all of our benchmarks. Okay, so now we took a look at how computer-aided programming can help simplify the development of concurrent programs. Now I want to showcase another application of program synthesis in systems development. And in this segment of the talk, I want to illustrate how computer-aided programming can help with security concerns. And to illustrate that, I want to focus on automatically generating sandboxes. And kind of to, as a brief introduction, as you all know, sandboxing is a widely used technique for mitigating many types of attacks. And in this segment of the talk, I'm going to be focusing on one simple but effective way to generate sandboxes, which is system call whitelisting. And the idea here is that basically the developer of the application writes a policy that describes all the ways this program can perform system calls. And if at runtime, the program makes some system call that's not allowed by this policy, the sandboxing framework will go ahead and terminate the application because that indicates that the program has been hijacked by an attacker. And in practice, system call whitelisting turns out to be effective because typically attackers exploit vulnerabilities in your code by using system calls in ways that your original program does not. So therefore, by writing these syscall whitelisting policies, you can substantially reduce the attack surface of your application. Now, however, even though syscall whitelisting is quite effective, programmers actually rarely write system call whitelisting policies. And in my mind, there are two reasons why that's the case. So first of all, programmers often don't exactly know all the ways their program uses these system calls, because a lot of these calls are actually made through third-party libraries, and you may not have a very good knowledge of the internals of all these libraries that you use. And furthermore, even in the case where you understand exactly what the library does, how it uses the system calls, you still need to write a policy in some domain-specific language. And generally speaking, there are basically a bunch of these policy DSL. So for instance, there is AppArmor, there is SC Linux and SecComp BPF, there is Pledge, and so on and so forth. Okay. So motivated by this problem, in our recent work, we looked at automatically generating these system call sandboxes, and we built a tool called Abaya that's described in our recent UPSLA 20 paper, which is called Automated Synthesis of System Call Sandboxes. And the idea here is our tool Abaya takes as input an unsandboxed C or C++ application, and it also takes as input a policy DSL, and then it outputs a system called whitelisting policy that has several nice properties. So first of all, Abaya guarantees that the policies it generates are sound, meaning that it will never terminate valid execution. So it will only terminate executions where the attacker is actually trying to do something bad. Another nice characteristic of the policies that are generated by Abaya are that they're precise, in the sense that it tries to constrain the system call usage of the application as much as possible in order to reduce its attack surface. And finally, I want to point out that Abaya is fairly general, in the sense that it's not customized for one specific policy language, but you can actually instantiate it across different syscall whitelisting frameworks. All right, so now before I explain how our technique works, again, let me show you an example. So let's say we want to generate a system called whitelisting policy for the well-known CAT application. And let's say we want to generate our policy in the Pledge policy language, or the policy framework targeting OpenBSD. And just to kind of, for those of you who are not familiar with Pledge, let me give you a very brief introduction. So Pledge is actually a very, very simple policy language, and all it does, it has a bunch of groups that tells you what capabilities the program requires. And Pledge has a total of 32 groups, but for the purposes of this example, I'm just gonna highlight 4 commonly used ones. So for instance, you may have we have a group called std.io, which gives you basically standard IO capabilities. There is a group called rpath, which gives you read access to the file system. wpath gives you write access to the file system, and cpath allows the application to create new files or directories. And as you might expect, the desired policy for the CAT application just consists of these 2 groups, std.io and rpath, meaning that we absolutely need to have these groups in order for the CAT application to do its advertised functionality, but we don't want to add any additional groups, because otherwise that just enlarges the attack surface of the application without adding anything. Okay, so let's take now a look at how Abaya actually works under the hood. So at a high level, Abaya consists of 2 phases. So in the first phase, Abaya performs static analysis of the input C++ application using abstract interpretation, and it outputs something called that we call a syscall invariant. And the syscall invariant is basically fed as the input to the synthesis engine. So basically this serves as the specification. And then the goal of the synthesis engine is to generate a policy in our specified policy DSL that's the best approximation of the computed syscall invariant. So in more detail, as I mentioned, Abaya performs static analysis using abstract interpretation. And for those of you who are curious, we use the reduced product of the disjunctive interval and array expansion domain. So this is not terribly important, but basically we found that the combination of these two abstract domains gives us a good trade-off between precision and scalability. And for example, here the computed syscall invariant looks something like this in the case of the cat application. So basically this is saying cat calls the, call the open system call, it can call sysctl, it can call mmap, and basically it's telling us all the arguments that these system calls can be invoked with. So for instance, it's saying that whenever we call mmap, the third argument should be either 0 or 3. So now based on the syscall invariant, we know that it is okay, it is legitimate for the application to make this system call because both the open system call and the arguments are actually allowed by our system call invariant. On the other hand, this system call is not allowed because according to our syscall invariant, the open system call cannot be invoked with argument 3. So this should be disallowed. Okay, so now once we compute our syscall invariant using static analysis, we feed this as the specification to our underlying synthesis engine. As I said, the goal here is to find a whitelisting policy in the given DSL that's the best approximation of the system call invariant. And in particular, there are two requirements here. The first requirement is that the generated policy should be sound, meaning that it should allow every behavior that's in our syscall invariant. Otherwise, we may erroneously terminate the application, which is of course not good. And in addition, we want to generate a policy that's precise. So we also have this optimality requirement. So basically that means for any other policy in this policy language, they should allow strictly more behaviors than the policy that's synthesized by our synthesis algorithm. So we want both soundness, but also optimality. And to solve this synthesis problem, we use a variant of the well-known CGIS or counterexample guided inductive synthesis paradigm that's adapted to guarantee optimality. And in a nutshell, as standard in CGIS, you have this interaction between an inductive synthesizer. In our case, this is based on search. And it interacts with a verifier. And in our case, the verifier is very simple. It just checks if the candidate policy is sound, meaning that it actually implies the system call invariant. And it also checks whether the candidate policy is optimal so far, meaning it's better than the policies that we've enumerated so far. And if it's unsound or it's suboptimal, the verifier is going to provide some feedback to the inductive synthesis engine. And the idea here is that the synthesis engine is going to leverage this feedback and it's going to use it to prune its search space. So it's going to block other unsound and provably suboptimal policies. All right, so now let's take a look at how Abaya works in practice. So actually, to evaluate Abaya, we did a fairly large-scale study, and in particular, we looked at 673 C++ applications targeting Linux and OpenBSD. And we also instantiated Abaya for two different policy frameworks. So one of them is seccomp BPF for Linux, and the other one is pledge for OpenBSD. So now to evaluate whether the Abaya generated policies are good or not, for seccomp BPF, what we did was the following. So for these Linux applications, we took proof of concept exploits targeting the Linux kernel, and then we checked whether the Abaya generated sandboxes are able to block these exploits. And what we found was that 96% of the Abaya generated sandboxes are actually resistant to over 95% of privilege escalation attacks targeting the Linux kernel. And for pledge policies, we did a different kind of evaluation. So since pledge is a simpler policy language than seccomp BPF, we were able to find significantly more manually written policies. So for this application, we actually compared the Abaya written policies with these manually written pledge policies, and we measured F1 score. And in a nutshell, what we found was that the Abaya generated policies actually do match exactly the handwritten policies for the majority of the benchmarks. And as expected, there were some discrepancies, and actually it turned out that some of these pointed to actually a bug in the manually written policy. So in one case, for instance, the manually written policy would erroneously terminate the application, and this was actually acknowledged and confirmed by the developers. Okay. So basically that kind of concludes my talk pretty much. So what basically the key takeaway from this talk at a very high level is that program synthesis is not just something that's useful for end users or non-programmers, but I tried to illustrate how it's useful across the whole software stack, going from data scientists to application developers to systems programmers. And as we saw in this talk, it's also useful for not just for functionality, but also for evolving and maintaining your software, for getting good performance without sacrificing correctness, and also for making your applications more secure. And before I conclude, I want to acknowledge all my collaborators. So of course, the lion's share of this work was done by my students and also former students, and also my other collaborators, such as Osber Bastani, Hovav Shakam, and Yanis Maragakis. So that's all I have. If you have any questions, I'm happy to take them.
Great, that was fantastic. Thanks, Işıl. Everybody can applaud on Slack. So there'll be some people typing in questions, and I'll go ahead and read them, and you can respond when this happens. I have a quick question. I mean, the work is super impressive and spans all these different areas. Where do you see like the next things? I'm sure you're working on some stuff right now, but where do you see like the next great places to apply program synthesis? And then where do you see like the technical challenges that remain? Like, what are the most exciting places to go? What are the maybe next obvious places to go? And what are the kind of like reach goals? Like, oh, if only we could do this, but there are some still significant technical barriers to overcome.
Right. So to answer kind of like your first question about kind of where I see this going. So if you've noticed, a lot of the techniques that I talked about deal with just a single form of specification. So one of the things that I'm quite interested in and have been exploring in recent work is what I call multimodal synthesis, where you basically take different types of specifications as inputs and like do synthesis from multiple modalities. That's one thing that I'm quite excited about. So for instance, in some of our recent work, we've also been looking at combining natural language with examples. That's an area that I think is quite exciting. Another thing that I'm excited about is kind of broadening the applicability of synthesis from just software development and looking at other application domains beyond programming languages. So for instance, in one of our recent works, we looked at combining program synthesis with traditional deep learning techniques to get to do traditional AI tasks like question answering in a more robust and also more data efficient way. That's another thing that I'm excited about. And I also think program synthesis has exciting applications in other fields like robotics. So those are kinds of the things that I'm interested in.
Cool. So can you talk a little bit more about the integration of deep learning for this question answering task?
Yes, certainly. So basically, a lot of the synthesis techniques that I've talked about here use a traditional programming language. But what we did in our recent work on question answering is we basically have some sort of neurosymbolic DSL where so we were focusing on the web question answering domain. So you want to answer questions for various websites, and we're assuming that these websites can have very different types of schemas, like global schemas. And basically the idea here is to combine traditional programming language constructs such as primitives for tree navigation and string processing with also deep learning modules from the NLP community for entity extraction, question answering, and so on. So that's something that we've been looking at.
Cool. Yeah, that's very provocative and interesting. So we have a question from Shaurya Patel. So he has two questions, really. So one is about, so they're both about concurrent program synthesis. So one is, how long does it actually take to generate the signals? And then the second is, can we do better in terms of performance than explicitly written concurrent programs? And I guess this is really about the abstraction. And he says specifically, like perhaps something like AutoTVM, but something that's not driven by target hardware.
Right, so these are excellent questions. So for the first question on generating the signal, so it of course depends on the application and how big it is, but you know, typically this is in the order of like minutes. So similar to the database application that I was talking about. And regarding performance, so in the prior technique that we developed, so it was competitive with handwritten code. But one of the things that we're currently looking at, so our main focus in that work was signaling, but not so much the lock placement. So the lock placement was done, basically, we were just inserting locks in a very coarse-grained way. So now what we're currently looking at is basically this interplay between the signaling and also fine-grained lock placement. So I think maybe by combining these two, we can actually perhaps do better than explicitly signaling code.
So to follow up along those lines, just hearing you talk about this and thinking about this problem made me think of some of the like genuinely horrifying things that happen in the Linux kernel, like RCU.
Right. That's actually another domain that we're looking at, exactly.
Oh, yes. Great. Yeah, so I mean, that's a perfect domain in my mind because it's it really is like a rocket scientists only allowed, you know, you have to be this tall to enter this ride. Notice that it's taller than me. Like I just find that stuff be out of reach.
Yeah, so whenever I tell someone about this work, the first thing they like, you know, especially systems people, oh, can you apply this to RCU? And that's certainly something challenging. I don't know this second how to do it, but that's certainly something that I'm very interested in and we're starting to look at.
Yeah, it's I think that anybody who's ever had to deal with like these super, what should I say, kind of scary synchronization primitives that can achieve, you know, significant performance advantages, but at what cost? You know, they're definitely dangerous.
Right.
So I actually, so somebody is typing in a question, but I want to ask another follow-up question. So I was intrigued by this, and I'll have to look at the paper, the neurosymbolic thing. When you have these things that come from like the NLP community, are you treating them as black boxes? You basically have some sort of like a library call and it goes and it does something and it returns something.
Yeah,
okay.
I was alluding to, we do treat it as a black box. And that's actually like asking, going back to the question that you were asking, that is actually a big challenge because, you know, how, you know, like all of these techniques are, you know, based on back propagation and, you know, so basically you need some sort of differentiable program representation to combine training with program synthesis. That is a very challenging and interesting, yeah, that's definitely a big technical challenge that would be very, very cool to solve, I think.
Right. Yeah. I mean, I think it's cool to see things kind of merging across these boundaries where you have, you know, traditional logic, and then you have this obviously something that's completely out there like deep learning. But, you know, if you can connect it up with differentiable programs, then maybe you can do something that's principled and that combines both. So that's pretty cool. So there's a question from He Wang. It says, for data wrangling, how do you train the synthesizer in general if you use machine learning? Could you give me a small example? Yeah,
so it depends really like what kind of training data that you have available. So in our, in this data wrangling domain, we actually did something fairly simple. So we were targeting the R language. So we basically looked at existing R programs and we did like a simple n-gram model. So it was nothing sophisticated. But for example, in, you know, as you know, there have been other work that uses actually deep learning, and we tried that, but that's all relies on kind of synthetic data because, there isn't just enough, enough real world programs. And if you want to throw deep learning at the problem, you probably need to use synthetic data.
Yeah, so you had mentioned actually earlier also, just very briefly, something about data efficiency. So is this specifically what you're looking at, some sort of way of learning, of extracting learning from a very, very small set of examples, or maybe you could elaborate a little bit more about that?
Yeah, I think combining program synthesis with deep learning is basically like, it's basically, in the machine learning community, people sometimes refer to as a few-shot learning. So I think this combination of program synthesis and pre-trained neural models, that basically gives you, in my opinion, an effective way to do few-shot learning.
I see. Interesting. Yeah, so I mean, one of the things that I always see, or I don't see enough of, I feel, although Lord knows the literature on ML is now completely intractably large, so I'm sure I'm missing tons of things. But we have programs and they're logical structures. We have things that we know about databases. Like there's a lot of knowledge that we don't have to learn.
Right.
And so it just seems like integrating those two things seems like a natural idea, but I see very little of that. And I see sort of like, we get a little bit of information here. Maybe we learn a little bit from positions or something and feed that in, or there's some auto encoding based on something, blah, blah, blah. But I wonder, can you talk about that?
And domain knowledge that we have. I mean, typically we don't build program synthesizers that work for arbitrary languages, right? You typically always have some sort of domain specific language, and that's where you build all your prior and domain knowledge. And I think, if you want program synthesis to be effective, at least in its current state, I think that's something we have to do, at least currently.
Right, that makes sense. Great. Okay, so we're past our time. I don't know, we don't have any more questions waiting, so maybe this is a perfect stopping point. So I'd like everybody on Slack to thank Işıl once again. Really great stuff. I look forward to hopefully having you come back and talk more about some of your other more recent work, which is all super cool and exciting.
Thank you so much for inviting me, Emma.